It is 7:10, so let's go ahead and get started. Just to start off, your tests are graded. I put them in the grade book last night. There was one question that I messed up when I made it up. It was fixed by the time you took it, but that I didn't give you enough information to actually figure out the answer. So that one I just gave everybody credit for. And so you'll notice that when you get your test back, and I will give them back at break time. And so we are going to cover 5.1 and 5.5 is how they have them numbered tonight, which is about systems of equations and systems of inequalities. So we're going to be doing that. And then remember, next week we'll have our test over these two lessons. And after the test, we'll review at the beginning of class. We'll have our test. After the test is over, we will spend some time, if anybody wants to, reviewing some of your old tests, because as I mentioned previously, your final will come from questions from your previous test. So if you want to get some of those questions answered from those tests, that might be a good idea. And that way you know what to study and stuff. And don't look at the review on the computer yet. That's not going to be accurate. I have to do some work with that to get it set up so that it has the types of questions that we went over. So don't worry about that review yet. So, but anyway, section 5.1, let's get started with this. Systems of linear equations. When we talk about systems, we're talking about multiple equations that get put together as a group. And our goal then, instead of just finding one answer that works for X or another answer that works for Y, is our goal is to find the set of answers that will make all of those equations or both of those equations true. In this case, we're only dealing with two equations, but it's going to make both of those equations true. So if we have a system of linear equations, if you graph them, what shape do you think they're going to make? Linear equations. They're going to make straight lines. So I'm going to draw our options first, and then we'll describe them. So one option for lines is you might have two lines, and this is probably the most common one. You might have two lines that intersect, right? The one point that they share in common, the XY coordinates for that point are going to be your X and Y values for the solution. Okay, so visually, that's what will happen when you get one answer. Okay, another option is we could have two lines that are, well, that's the best I can do. They're parallel. And when you have parallel lines, what do you know about parallel lines? They never intersect. So that means there will be no solution to that system. There are no XY coordinates that will make both equations true. Okay, so it's impossible. Then the last case is you may have two lines that actually completely correspond with each other. So every point on one line is part of the other line because they're actually the same line. Okay, so these two are kind of special cases. The one where the two lines intersect in one point, that's probably the most common case, but these are two special cases that we will take a look at tonight. So let's get to this. So exactly one thing will happen of these following ones. The system has exactly one solution. That's the top one. That's the most common one that we deal with. A system that has a solution is called an independent, it has exactly one solution is called an independent system. An independent system. Another option is the parallel lines one. It might be that a system has no solution. That is called an inconsistent solution. Or sorry, an inconsistent system. Inconsistent system. And then the last one, the system has infinitely many solutions because every point on one line is a point on the other line, so it has infinitely many solutions. That is called a dependent system. So independent and dependent, there will be solutions. Independent only has one solution. Dependent has infinitely many solutions. Okay, everybody got that written down who wants to? All right. So we are going to learn two methods tonight. We're going to focus on two methods of solving these linear systems. The first method is what we call the substitution method. And I'm sure that you've probably heard that word before, especially if you were in sports. When you have a substitute, what happens? One person is replaced with another person, right? Now in math, when we substitute, it has to be one thing is replaced with something that's exactly equal to it. Because we have to be very specific. That doesn't happen in sports. Usually you replace one person with another person. It's not exactly the same person, right? So, but the substitution method, here's how we use the substitution method. You have to take one of those equations and solve for one of the variables. It doesn't matter which equation you choose. So my suggestion is if you're going to use this method, that's loud. If you're going to use this method, if you're going to use this method, pick the one that you think is going to be the easiest one to solve for. And when we say solve for, it means get it by itself. Okay? So if you're solving for y, it means you're going to get the y by itself. If you're solving for x, it means you're going to get the x by itself. And you just have to do that one time. Okay? Now, after you do that, you're going to substitute. And you substitute the expression you just found in step 1 into the other equation. You have to put it into the other equation, not into itself. Okay, so you put it into the other equation, and then you will get a new equation that only has one variable. And that's our goal, to get just one variable, because initially we're going to have two variables. And you'll see that in just a minute. Then you'll solve for that variable, and you'll get whatever that variable is equals a number. And then once we know what that number is, we call this back substitute. You take that number, and you substitute back into the other equation. Or actually, either one of the equations from the very beginning, from step 1. The easiest one to plug it in is the one that you solved already in step 1. But you could actually put it back into either equation. Once you do that, you'll have one variable again, and you'll be able to solve for that second variable. And once you have both of those variables, you're done. And on these, write down as many of these words as you need to. You don't have to copy the whole thing word for word, just so you understand what you're supposed to do. Sometimes it's harder to explain in words rather than just to watch an example and figure out, oh, that's what I'm supposed to do. Right. Let's go ahead and talk about the other method right away, and then we'll do some examples of each of these. The other method is what we call the elimination method. And in the elimination method, the first thing we do is we adjust the coefficients. Now, if you remember, the coefficients are the numbers in front of the variables. Okay? So the way we're going to adjust the coefficients is we are going to multiply the entire equation, or maybe either one entire equation or both entire equations by some number, so that we can match up some of the coefficients so that they're exact opposites of each other. Now, we're not going to be able to typically match up all of them, but we just want to match up one set, either the x's coefficients we want to be opposites or the y coefficients we want to be opposites. It doesn't matter which one, just need to get one of them matched up. And again, I'll show you an example of this as we go through it. Once you have them matched up as opposites, you're just going to add the two equations together. And what happens when you add opposites together? It becomes 0, right? If you add a 5 and a negative 5, you get 0. If you add a 10 and a negative 10, you get 0. If you add a 2 and a negative 2, you get 0. So the reason that we're going to get them to be opposites and then add them is because you're going to have 0 x's or 0 y's, one or the other, and then that's going to go away. They cancel out. Once that one variable is eliminated, that's why they call it the elimination method, then you solve for the variable that's left. And once again, we do that back substitute idea. You're going to substitute back in. Once you know that answer, you're going to plug it in and be able to figure out the other answer as well. They're pouring in now. Okay. So let's take a look at some examples. And I put on there to describe the lines that we would graph. Remember, we had those three types. You had two lines that intersect. That meant one solution. You had two lines that were parallel. That meant there were no solutions. And then you had two lines that were actually corresponding with each other. That means there's infinitely many solutions. So let's take a look at these examples. I'll let you write it down first, or this example.
Will this be the substitution?
Yeah, and I'm going to do this one with substitution, and I'll explain why I would choose substitution on this one. Because you can really, well, you could actually use either method here, and it wouldn't be too bad. But I want to show you both substitution and elimination. Okay, so we can, like I said, we can use either method, and I'm going to do substitution on this one. So in substitution, we have to get one of the variables completely by itself. Do I need to read this so you can see it? So you can know what it says? Would that be helpful or no? Yes?
No, I got it.
You got it? Okay. All right. And the spread out room, it gets back far. Okay. So we've got 3x minus y equals 0. We've got 5x plus 2y equals 0. If I'm going to use substitution, I'm going to try and pick the easiest variable to isolate or to solve for. And in my opinion, that's going to be this one right here, the y. Now, the reason I think the y is the easiest is if I try and solve for any of the others, I'm going to have to divide with this one. I would have to divide everything by 3, right? That's going to give me fractions. I don't want to have fractions. Here, I would have to divide everything by 5. That's also going to give me fractions. I don't want to have fractions. Here, I'd have to divide by 2. That'd be fine over here, but it would make a fraction out of this. So if we can avoid fractions, I mean, how many of you love fractions? Come on, everyone. I know you all love fractions. Okay, I know you probably don't love fractions. But let's avoid the fractions if we can help it, right? So let's stay away from them. So I'm going to get that y by itself. And probably in this case, the easiest way is just to add y to both sides of our equation. So notice that cancels out, and now we have 3x is equal to y. Does that make sense? We can get the y by itself that way. Now, there are other ways, but that's probably the quickest way. You could have subtracted 3x and then divided by -1. That would have also worked. And sometimes we kind of get in a habit, and maybe that's what we do, and that's fine. You'll get the same answer. Okay, so that was step 1. Solve for one of the variables. Step 2 was to do the substitution. So right here in the second equation, so right now in this, right here in the second equation, we're going to write down 5x plus 2, and I'm going to put a parentheses in place of the y, equals 22. And what are we going to replace the y with? 3x, because we know that y equals 3x, right? It's like if I give you $1 and I say, can I have 4 quarters? If you have 4 quarters, you're probably okay with that because they're equal, right? So since that's equal, we can replace that. Okay? Now we still have 5x. And then what do we have here when we multiply this together? 2 times 3 times x is 6x. Okay? And then 5x plus 6x is 11x. Okay? And then finally, how do we get the x by itself? Divide by 11. So now we get x equals 2. So that was step 2. Once we substitute, solve for that variable. Okay? Did we have 4 steps or just 3? I think we just had 3, right? Okay. So substitute and solve. That gives us this. Now, once we have this, we go back up to here. Right? That one that we solved right away. And what do we know? Now we know x equals 2. So that tells us, since y equals 3 times x, now we know y equals 3 times what?
2.
2, because x equals 2. And so that tells us y equals 6. 3 times 2. So the way we write our answer, we know x equals 2, and we know y equals 6, and we can write it as an ordered pair. Remember, the first number is always the x, the second number is always the y. Now, can anybody just in general describe the lines that we would draw if we were going to graph this? Not open circles. I mean, we're just drawing two lines. So we're going to draw two lines. Are those lines going to intersect? Remember our three options? For those of you who are here, they might intersect in one spot, they might not intersect at all, or they might completely correspond with each other. Okay? If you get one solution, that means you're drawing two lines that intersect in one spot. That one spot is this solution. So we're actually drawing two lines that intersect at the ordered pair 2, 6. Okay? Now, one more thing we want to point out. If we want to check our answer to make sure that we're correct, what should be true here? When I take this x and this y value, if I plug it back into both of these, it should make them both true. Okay, I'm not going to check everyone, but let's check this one just to show that. So our first equation, 3x minus y is supposed to equal 0. We've got 3 times 2 minus y, which is 6. Is that a true statement?
Mm-hmm.
Yeah, 6 minus 6 is 0. So this one works out. The other one says 5 times x, which we said was 2, plus 2 times y, which we said was 6, is supposed to equal 22. Well, that's 10, and this is 12. Is that a true statement? Yeah. So that is the one point that will make both of these equations true. That is our solution to this system. Okay, and like I said, most of the time when we do these, we're going to have that one solution. Okay, so that's an example of the substitution method. And I'll be honest, I like the elimination method better. But there are certain times when I will use substitution, and I'll kind of show you that as we go through here. Okay, so we've got 2, 6, and that is because it just has one solution. That is an independent system. It's those two lines that would intersect just at one point. Okay, so does that make sense on the first one, that example? All right. All right, the second one, we've got this system. And in this case, this is definitely one I would use elimination on. So let's do an example of elimination and go through this. So with elimination, I maybe should have started with an easier one. But with elimination, remember our goal is to get either the x's coefficients or the y coefficients to be exact opposites of each other. Okay? So what we have to do is we have to look at the x's, and again, choose the one you think is easier. We look at the x's, and we look at the y's, and we say, okay, which ones do we think we could make opposites of each other using multiplication? And you haven't done this for a while, if you remember, if you've done it before at all. But so here's the idea. I, a lot of times, will kind of pick the smaller ones because smaller numbers are usually easier to work with. And I'll look at this 2y and this 3y, and I'll say, oh, using multiplication, what can I make both of those into? What is what's a multiple of both 2 and 3? What? 6, right? 6, not a factor, a multiple. So I can use multiplication to make this into a 6, and I can use multiplication to make this into a 6, right? Now I do want one of them to be positive and one to be negative. And so it's really good that the 2 is already negative and the 3 is already positive. So that's a good thing. What would I have to multiply by to make this 2 into a 6? A 3, right? And so I guess a negative 6. I'd multiply by a 3 to make that a negative 6. And what would I have to multiply this positive 3 by to make it into a positive 6?
2.
A 2. And when we do that, we have to multiply the entire equation by these numbers. Okay? So here's what this turns into. 3 times 8x is 24x. 3 times negative 2y is negative 6y. So you have your equal sign. 3 times 5 is 15. Then we do the same thing with the other one, only we're using a 2 this time. 2 times negative 12x is negative 24x. 2 times 3y is 6y. And we have our equal sign, and then 2 times 7 is 14. Okay? And then if you remember what our next step was, we're going to add these equations together. Now, I do want to pause for a second, because the reason we can add these together is something that I want to make sure that we understand. So think of an equation like kind of like a teeter-totter. You guys know what teeter-totters are? Or balance, right? If you've got two people on a teeter-totter and the teeter-totter is balanced perfectly, okay? So that's one situation. And then you've got another teeter-totter with two different people, and that one is also balanced perfectly. Okay? So the idea is these two people, if they're the same distance away from the center and everything, these two people weigh the same, and these two people weigh the same, right? What happens if you take the two people from that second teeter-totter and put them on the first teeter-totter with the first two people? What's going to happen to the teeter-totter? It'll still stay balanced, right? Even though we're adding in that other quote-unquote equation, that's what we're doing here. When we add these two are these two are equal and these two are equal. When we add them, the result will still be equal. Okay? All right, so now let's do that. Something unique is going to happen here. This is going to be one of our special cases. What happens when we add 24x and negative 24x? What?
Cancel.
It cancels. It becomes 0x, right? So this just cancels out. What happens when we add negative 6y and positive 6y? That cancels also. So we end up with 0. 0x plus 0y is just 0 on the left-hand side. What happens when we add the 15 and the 14? We get 29. Okay, now this is a little bit weird because all the variables are gone, right? And are we left with a true statement or a false statement? This is a false statement. What do you think that might mean? There's no solution. What that means is it doesn't matter what x values and y values you put in, there's no way that it can work for both of these equations. Okay, so that's one of our special cases. So if you think about the lines, no solution, what are the lines going to look like if we graph them? It'd be parallel lines.
Parallel.
They would never intersect. Okay, that's the idea here. So they'd be parallel lines, no solution, and so we say that this is an inconsistent system if there's no solution. Okay, so no solution, that's an inconsistent system. And again, if we were graphing it, that would mean that we have two lines that are parallel to each other. Now, just so that we've talked about it, if we would have a true statement right here and all the variables canceled out and it was a true statement, that's that one where they're actually the same line. And so that would mean infinitely many solutions. And we'll hopefully, I think we have one like that after a while here. Okay? And even though we didn't get an answer, that's the process we use for elimination. Okay? All right, let's try another one. Right. So just one thing to mention, on your test, I am not going to specify which method you use. I'm not going to say use, on the homework it does say use substitution for these, use elimination for these. On the test, I'm not going to tell you which one to use. You can use either one. In fact, every one of these problems you could do by substitution, and every one of these problems you could do by elimination. Okay? So I guess that gives you a little bit of an option. If you like one method better than the other, just really practice and get really good at that one. But I will tell you that sometimes elimination is easier and sometimes substitution is easier. So the goal is that hopefully you know how to do both. But if you're, as far as studying for the test, get really good at one of them, and then you can use that one pretty much every time if you want to. Okay, so as I look at this, here's what I look for. Again, since I prefer elimination, if I look at the system of equations and one of the variables is not already by itself, I pretty much always do elimination. Okay, so in other words, if I don't see y equals or x equals, I'm going elimination because I like elimination better. Again, you guys can use whichever method you want. So as I'm looking at this, I'm going to say I think elimination would probably work better here, in my opinion. But in this case, I think this is another one of our special cases. I want to show you what happens with substitution also, so that you can see both of those options. Because we did an elimination that was a special case. I want to show you a substitution that's a special case also. So looking at this and looking at these variables, if we're going to do substitution, we want to solve for one of the variables. What variable do you think is going to be the easiest one to solve for? Okay, but which one?
3x minus 6.
Okay, and which variable are you going to solve for if you're using the 3x minus 6y equals 12?
3x.
The x, right?
Yeah.
Because if I divide by 3, 3 goes into 6 evenly, right? That's a good thing. And 3 goes into 12 evenly. That's a good thing. So sure, let's solve for the x. So the first thing we would do is what? If we're trying to get this x by itself.
Plus 6y.
You add.
Okay, I think I heard a lot, but I think I heard add the 6y,
Add 6.
right? So let's add the 6y here to cancel and here. That gives us 3x equals 6y plus 12. Okay, good so far? Then what else do we have to do to get that x by itself?
Divided by 3.
Divide by 3. And we have to divide everything by 3. So that will give us x equals 6 divided by 3 is 2y, and then 12 divided by 3 is 4. Okay, so are we good so far that we have now solved for the y, or sorry, for the x? Okay, now we're going to substitute, but we have to substitute into the other equation. If you substitute back into itself, it always turns out the same way, and it doesn't tell you anything. Okay, but let's substitute into the bottom one. So we got the x by itself, so we're going to have 4 times x minus 8y equals 16. What are we going to replace the x with?
2y plus 4.
Yeah, from over there, right? The 2y plus 4. Does that make sense? Because we know x equals 2y plus 4. Is everybody okay with that? So we're going to go 2y plus 4 is replacing the x that used to be there. What do we want to do next? Multiply what? By what? Yeah, we want to distribute. Yeah, I thought that's where you're going. I just want to make sure. So we're going to distribute the 4. 4 times 2y is going to be 8y. 4 times 4 is going to be 16. Then we have minus 8y, and we have equals 16. So we distribute to get rid of the parentheses. Now notice we have like terms. We have an 8y, and we have a negative 8y. What happens when we add those together? They cancel. So once again, all of our variables went away. We have 16 equals 16. Is that a true statement? Yeah, that's a true statement. Okay, and that tells us this is one of the special cases when all the variables go away. But this time we got a true statement because they're equal to each other. It's a true statement, 16 equals 16. So this is a situation where we have infinitely many solutions. And what that means is these two equations right here are actually describing the exact same line. If you would graph each of them, you'd graph the same line twice. Okay? Now, we do want to describe our solutions, right? But there's infinitely many. So here's how we describe our solutions. Well, this one was unfortunate. It solved for that one. But anyway, so notice we had already solved for the x over here, right? And the x is set up that if you know what y is, you can figure out what x is, correct? So this might be different than the answer I have on here because you can do this kind of different ways. But here's what we do. We want to describe the x and the y coordinates. But there's an infinite number of them, so we can't just say like 5, 6, and 2, 3, and whatever. That would be impossible to list them all. Does that make sense? So we kind of describe the pattern, and here's the pattern. The pattern is we can choose any number that we want to be y. And a lot of times they'll use a, I think, for any number. Okay? Once we've chosen that y value, if we replace the y with the a, the rule is the x value will have to be 2a plus 4. Okay, so what that means is that's just a rule that describes all the solution values. So if y is a 1, then x would have to be 2 times 1 plus 4. It'd have to be 6. If y is 0, then this would have to be 2 times 0 plus 4. It'd be 4. 4 comes 0. So you see that we could get any number of solutions. We just pick a different number for y, and we plug it in, and we get an answer for x. So this is the type of answer we will get if there are infinitely many solutions. And again, if we graph that, those two would be the same line. Okay. Now, I think I probably did this differently here. Yep. So notice with this one, I chose an x value. Okay. If we would have rearranged this equation and gotten the y by itself, it would have said y equals 1/2 t minus 2. Oh, not t, x, sorry. Okay, if we would have gotten the y by itself, we would have had a fraction. Like I said, we don't usually like the fractions, so that's why I do it the other way. But if we had solved it this way, notice then we pick any value we want for x, and we would put that in here, and then we replace the x with that value that we choose. In this case, I chose a t, but it's the same. It's just a different description of the same line. Okay. The reason a lot of times people will use this is because this is slope-intercept form, so it helps you graph the line right away if you want to, if it's written like this. Remember we talked about that? The -2 would be the y-intercept, and the 1/2 would be the slope. That was a long time ago, but hopefully you kind of remember it a little bit. Okay, so again, we would get all the same ordered pairs. It's just a rule that applies to both. Okay, and so you do still want to describe your solutions, even though you have infinitely many, but you have to use a general expression to describe them. Okay, and that, remember, as we call it, a dependent system. All right, we didn't get rid of it. Everybody loves fractions, so let's take a look. Since everybody does love fractions so much, when we see a problem like this, my suggestion is, first step, get rid of the fractions. Because we know we don't like them. And I think we did this, again, I think we did this quite a while ago at the beginning of the semester. Does anybody remember how, just looking at the top equation, how we could get rid of these fractions? You're on the right track, but the problem is you've got two different fractions. So a reciprocal would maybe fix one of them, but not the other one.
So it would be like the other one where it has to equal, say 15.
Yeah. We multiply by the number that we need to cancel out both of these denominators. So does everybody see that on the first equation, if we multiply by a 15, it will cancel out the 3, and it will cancel out the 5? Okay, and so what I'm going to do is I'm going to put the 15 by each one of these, so we realize that we're multiplying each thing by 15. Okay, and let's go ahead and do that. So if we multiply 15 times 2, does it make sense that's 30? And 30 divided by 3 is 10. So this becomes 10x, and then we have minus. Then 15 times 1 is 15 divided by 5. What is that? 3y equals, and 15 times 3 is 45. There's nothing to divide by there. What do you think we should multiply by over here? We could use 8, but we can go smaller. We can multiply by 4. That will cancel both of these out, right? Does that make sense? We want to cancel out the denominator so that they're not there anymore. Notice this one looks much nicer now, no fractions. Okay, so multiply by 4, multiply by 4, multiply by 4. 4 times 1 is 4, divided by 2 will be 2x. I'm going to put it up a little higher here so that they're closer to each other. 4 times 3 is 12 divided by 4. That's going to be 3y. Oh, that's convenient. And then 4 times 1 is 4. Now, what did I see that made this so convenient? The 3's are already opposites, right? I didn't know that was going to happen, but it's really convenient that it did happen. So notice we don't have to multiply by anything. We can just go directly to the elimination method and add these together. Does everybody see that? As long as those coefficients are exact opposites. So we're going to add these together. What do we get when we add the 10x and the 2x?
12x.
12x. We said those are opposites. They're going to cancel to be 0y, which is just 0. And then 45 plus 4. Well, that's not as nice. That's 49. Okay, and the reason I said it's not as nice is because what is the next thing we're going to do? Divide by 12. Man, the fractions came back. 49 over 12. Now, here's the deal. Do not round this off. I know that we put these things into our calculators and we love to round them off. Do not round them off because you're going to mess up your second answer. Okay, leave it as an exact fraction, 49 over 12. Now, what do we do with that 49 over 12? We haven't had to do this with the elimination method yet.
Replace it with that.
Yeah, we're going to substitute in for the x. Now, it doesn't matter which of these two equations we plug it in for. I wouldn't go back to probably the fraction ones unless you really, really wanted to. I'd use one of these two. Does anybody have a preference of which one they'd like to try?
The bottom.
Why the bottom one?
It's not negative. I don't know.
Okay, it's not negative. That's one reason. I would choose the bottom one also, but for a different reason. The numbers are smaller, right? I think that makes it easier. So choose the smaller number. So here's what happens. We're replacing the x with 49 over 12 and plus 3y equals 4. You could have done the top equation as well. It doesn't make any difference. Now, 2 times 49 over 12. I'm guessing that most of you have calculators. You can probably just do this. It's going to end up being 49 over 6. If we leave it as an improper fraction. And I am going to leave it as an improper fraction because eventually we're going to have to divide, and that's just easier with improper fraction. What are we going to have to do next if we're trying to get that y by itself? Yes, not the 3y. Subtract the 49 over 6, right? Because we're trying to get the 3y by itself. That will cancel. Again, if you want to use your calculator for this, you may. But if we're adding this or subtracting this without a calculator, we need what we call a common denominator. And our common denominator would be the 6. So if you remember this from way back when, that's how you make a denominator. You multiply by, in this case, 6 over 6 to get a denominator of 6. That means this will be 24 over 6 minus 49 over 6. And when we add those together, we get negative 25 over 6. Because the denominator doesn't change, you just do 24 minus 49. And then our last step to get that y by itself, divide by 3. And that's normally what we think. And with your calculator, you're probably fine to do it divided by 3. But if I'm doing this by hand and I see fractions, instead of dividing by 3, does anybody know what our other option is? All right, then we're going to learn something new. You can multiply by the reciprocal. Do we see that if we multiply 1/3 times 3, that's still going to cancel out to be a 1? Okay, so we're going to multiply that on both sides. So now we get y equals negative 25 on the top, and then we just multiply straight across, so we get 18 in the denominator. So now we have our two answers. 49 over 12 is the x value, negative 25 over 18 is the y value, and that would be our solution. So if we get one solution, what does that mean about the lines? They're going to intersect in that one point, right? And now if you really wanted to think about it, this is just a little bit more than 4. It's 4 and 1/12. This is kind of like negative 1.5. Not quite, but almost negative 1.5. Okay. So hopefully we did all our work right, since we got fractions. And everybody gets nervous when we have fractions, including me sometimes. So, okay, 49 over 12 and negative 25 over 18. Okay, but again, that means it's a consistent system. It has one solution. Two lines would intersect. Okay, so if you've got fractions, they won't always come back, by the way. Sometimes they are gone. But try to get rid of them first because it's easier to do the math without fractions, right? This part right here was much easier than this part over here, correct? And less scary too. But try to get rid of the fractions, and sometimes they come back and you can't get rid of them completely, but sometimes they don't. So, all right, let's try another one here with some fractions. Only one of them has fractions this time. Okay, so using what we just talked about, and that, just so you know, it says 1/2 x minus 1/3 y equals negative 1. And then 2y minus 3x equals 6. So using what we were just talking about, what do you think we might want to do here? Okay, eliminate, but what even before that? Get rid of the fractions. How can we get rid of the fractions this time? Will 6 cancel the 2 and the 3? Yes. So let's multiply just the top one by a 6. And so we're going to multiply everything by 6. That will give us 6 times 1, and then divided by 2 is 3x. 6 times 1, and then minus. 6 times 1 divided by 3 is going to be 2y. And then 6 times negative 1 is minus 6. Now our denominator, our bottom one, oh, look at what happened here. You see the order is reversed? Let's line it back up. Okay, let's put the x's first. We're going to have negative 3x. We're going to have plus 2y. And we're going to have 6. Okay, what do you see that happens here? This cancels, that's a 0 equals 0. What does that mean? Be careful. Is it a true statement or a false statement? 0 equals 0, that's true. So what does that tell us? It's infinitely many. These are actually the same line. It doesn't look like the same line because of those fractions, but once we get rid of the fractions, we find out, oh, it's actually the same line. So here's what we're going to do. Let's take this equation right here, 2y minus 3x equals 6. And this time, let's go ahead and put it in slope-intercept form. So let's get the y by itself. So what would we do first to get this y by itself? Add 3x. So 2y equals 3x plus 6. Then what? Divide by 2. And we're going to divide everything by 2. That gives us y equals 3/2 x plus 3. Now, if you did the same thing with this one up here, you get the same answer, right? Because they're the same line. All right, so how are we going to write our solutions? This time we get to choose a value for x. What variable do you want to use? P. P, all right. P for, I don't know what, something. Once we know that x is equal to p, what does y have to be equal to? Remember what happens. We chose that x is going to equal p.
To p.
So it's going to be 3 over 2 times p plus 3. And you can choose whatever variable you want there. You're just saying it can be any number. We can pick any number we want. And then once we choose that, automatically y has to be this. Right? So if I pick the 12, you plug it in. If I pick the negative 18, you plug it in. And you're going to get your y value. Okay, so again, those are two equations that are actually the same line. So that's a dependent system, and we get our answers there. And I use T for that one. Okay, does that make sense? So we've seen that special case a couple of times, sometimes with elimination, sometimes with substitution. But the whole deal is the variables will go away in those special cases, and you're going to be left with either a true statement or a false statement. Like 0 equals 0 is true, 16 equals 16 was true, but 0 equals 29, that's false. And that was a no solution. Okay? All right. So we did some substitution, we did some elimination. And again, one of the key reasons that we learn about these things is word problems. And we call in math, modeling is when we take an equation and set it up so that it applies to a specific word problem. So here's our guidelines for modeling with systems. First of all, you want to identify the variables you're going to use and what they stand for. Okay? So identify the variables you're going to use and what they stand for. Usually, the question tells you what your variable is going to represent. Like if the question says, blah, 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 find out how many hours something happened. Well, you're going to choose a variable that represents hours, right? Does that make sense? All right, next. Express your unknown quantities in terms of these variables that you have chosen. And usually you'll have like one sentence that talks about one part and another sentence that talks about your other equation, and you put them together and then you have two equations. Once you've done that, you're going to be able to set up your two systems. Like I said, usually that happens with two separate statements. A lot of times it's two separate sentences. And then we're going to solve the system and interpret our results. In other words, it's not good enough if you have a word problem to say, oh, x equals 5 and y equals 10. The question is, how does that answer the situation that we're dealing with? So you want to say, oh, there were 13 marbles and there were 10 coins in the bucket, or who knows what. Okay, are we good to go on? All right. Do not try to write down this example because these are word problems. I can't have to write down the whole thing. If you're going to take a picture of it, that's fine, but I will post the video as soon as I can tomorrow because I know a couple people were gone and they are going to need that anyway. So, example 6, a local buffet charges $7.50 per person for the basic buffet and $9.25 per person for the deluxe buffet. If 27 diners went out to eat and the total bill was $227 before taxes, how many chose the basic buffet and how many chose the deluxe buffet? Okay, so do we have a kind of a picture of what's going on here? You got a bunch of people going out to eat. Some get one sort of a buffet, some get the other one. One maybe has seafood with it and the other one doesn't. Or maybe one has a drink and the other one, I don't know, whatever. So the first question we kind of have to ask is, what are the variables going to represent? What makes sense from the question that they're asking us? What should our variables represent?
The 750.
Okay, what about the 750 and the 950?
They're different.
Okay, and so, like, let's say one person goes and they get the 750 buffet, right? What happens if 5 people go and they get the 750 buffet? What would you do? Or how much would they have to pay total? I'm just giving you a separate. Okay, let's make it easier. Let's say you go to Walmart and you're buying Dr. Pepper. And just for ease of calculation here, each 24-pack of Dr. Pepper is on sale for $5. How much do I have to pay if I buy 2 of them? $10, right? How'd you get that?
You added the
5 plus 5. What if I bought 10 of them?
10 times 5.
10 times 5. Do you see that it's the number that you buy times the price? Right? So they told us the price. What do we not know? We don't know how many people bought the deluxe and bought the basic, right? So let's let our variables represent how many chose the basic and how many chose the deluxe, right? See how it's in the question? So what variable do you want to use for the number of people who chose the basic? Let's use B. That's a great plan. I'm going to use B. How about for the number of people who chose the deluxe?
C.
Let's go with B. That helps us remember, right? Okay. So now this is B is the number of people who chose the basic buffet. D is the number of people who chose the deluxe buffet. All right. Let's read through this again and see if we can come up with some equations that will help us. A local buffet charges $7.50 per person for the basic buffet and $9.25 for the deluxe buffet. Well, that gives us information, but nothing really pertaining to an equation. The next statement, if 27 diners went out to eat, what does that tell us?
There's 20.
27 total people. Does it make sense that that means B plus D has to be 27? Does that make sense? Because you put the basics and the deluxes together, you get 27. Right? Now let's think about the next part. And the total bill was $227. Now remember our Dr. Pepper and Walmart example. You guys said that if I bought 10 24 packs of Dr. Pepper at $5 each, I would have to pay 10 times 5, right? Or 50. Does it make sense that the amount of money paid by these people is going to be $7.50, the price for one of them, times B, however many of them went there? Right? Like the $5 times 10 24 packs. So $7.50 per person, and this is how many people got that. Right? So if there were 12 of these people, it'd be $7.50 times 12. If there were 15 of these, it'd be $7.50 times 15. So that's going to be the amount of money paid for the basic buffets, $7.50 times B. Plus, how much did the people pay who went for the deluxe buffet? $9.25. And how many of them were there?
We don't know.
D number of people, right? So it's going to be, you're right, we don't know yet. Hopefully we're going to figure it out. $9.25 times D. That's how much money they had to pay. Does that make sense? And then what was the total amount of money that the people paid?
$227.
$227. Do you see that now we have a system of equations? Okay, so now we're going to do exactly what we have been doing for the last whatever amount of time. What do you guys think you would do here? Oh, guess and check. You could. Might take a while. Let's see, 1 and 26, 2 and 25, 3. Okay. But if we do it mathematically, does it make sense we could use either substitution or elimination here again? Which one do you guys want to try?
Elimination.
Elimination. Okay. She said elimination first. I don't know if you said substitution, but that's what I heard first. So if we're going to do elimination, we want to get the variables to match up as opposites, right? So which one is going to be the easiest one to match up here? Top one. And what are we going to multiply the top one by? We actually have two options here that are equally easy. I want to match it up with this or this, right? And these are both just ones. So either I multiply by a negative 750 to match it up here as opposites, or I multiply by a negative 925. Let's go with the smaller one. Sounds like a good plan. So let's multiply by negative 7.5. I'm going to need your guys' help here with this 27, I think. So that's going to give us negative 7.5b minus 7.5d equals, can somebody help me out with negative 7.5 times 27? I see some calculators, so I know I've
202.
one more time.
Negative 202.
Negative 202.25? No, 0.5. Okay. And you see that we don't really need the zeros on the end, right? Because it's after the decimal point. This one we're going to leave alone, but I'm not going to put those zeros on this time because we don't really need them. Plus 9.25b equals 227. Okay, remember now with elimination, we add them together. Whoops, I forgot my negative. So what happens with the b's? They cancel. That was the whole point of multiplying by the negative 7.5. What do we get? And again, you may want a calculator for this. What do we get when we add the d's together?
You divide. Oh, never mind.
Not yet. We're just adding right now.
You get 2.
I think it's 1.75.
Yeah, 1.7.
1.75. And then here, what do we get when we add these two? I think that's going to be negative 20 or 24.5. Can somebody check that? Is that right?
24.5, yeah.
Okay. And then now we're ready to get the d by itself. So what do we do? Divide by 1.75. I hope this comes out right. Otherwise, we're going to have a half a person eating the buffet. 14?
Yeah.
That's a good number because at least that means it's an even number of people. We don't want to have 13 and a half people eating a certain buffet. And okay, so 14 people ordered the deluxe, right? What does that mean about how many people, whoops, how many people ordered the basic? Well, we could go back and actually try and do it mathematically, but isn't total of 27 people? 14 got the deluxe. How many people are left, right? So you're correct. It's going to be 13 people got the basic and 14 people got the deluxe. Okay, but again, don't just write, oh, B equals 13 and D equals 14. Okay, you want to explain kind of the answer to the question. 14 people got the deluxe and 13 people got the basic. No, great question. I can't remember. I can't remember. I think they usually have a box that says this many people, like in this case, this many people got the deluxe buffet, this many people got the basic buffet. So you just have to put it in the correct box.
I have a question.
Yes, ma'am.
Why did we do the negative 7.5?
Okay, so who can answer that question? Why did we do a negative 7.5?
Because it was the smallest one that we could
Okay, it was the smaller one between the 750 and the 925. But the reason, are you wondering why we chose a negative? Or
Yeah.
why it was 750?
Yeah, no, the negative.
Okay, it's a negative because we want these two to be opposite signs so that when we add them together, they cancel out to be a 0. So we always need one of them to be positive and one to be negative. So if they're the same, we've got to multiply, like these were both positive, so that's why we had to multiply by a negative to make one of them positive, one negative.
Okay, that makes sense.
Okay, and again, the whole purpose is so that they cancel out to be a 0. Okay. All right. So yeah, we got the basic 13, the deluxe 14. All right, let's do one more. This one is a little bit tougher, just because you have to kind of think about it. I know thinking with word problems can be difficult. So this one says a 10% salt solution is to be mixed with pure water to produce 75 gallons of a 3% salt solution. How much of each is needed? Okay, so here's the idea. We've got these two. I'm going to draw a picture. You're going to be amazed at my artwork. We've got pure water. We've got an empty jug, and then we've got some sort of solution that's 10% salt. Okay, does that make sense? Now, we're going to mix these together, but we can't just mix all of it together. We have to mix them in a certain way so that we end up with 75 gallons of solution that's 3% salt. Okay, does that make sense? So the idea is, so let's see if we can think of what would be a good example. Okay, so just so you know how cheap I am. When our kids were little, we would buy juice, and they drink juice like, you know, pigs. So what you do is you mix the juice with the water, right? So that it lasts longer, even though it doesn't taste as good. I wouldn't drink it with the water. I'd give that to the kids. I'm like, whatever. So anyway, so the idea here is, what happens to the juice when you mix it with water? It's diluted, right? There's less juice concentration.
It's better for them too.
It's probably better if it doesn't have as much sugar, right? So there's probably other reasons other than I just don't want to spend a ton of money buying juice. Okay, so we mix it together, and you know that juice concentrate that they used in the first place to make the juice, which they mix with water, now I'm mixing it with more water. So it maybe was 10%, or it was maybe 80% juice before, but now I'm mixing it with water, and now maybe it goes down to 60% juice. Does that make sense? So that's kind of what we've got here. We've got 10% salt. We don't want it to be this salty, so we're going to mix it with water to make it less salty. Does that make sense now, kind of? Okay, so that's the kind of the picture that we've got. All right. So let's see if we can set this up. How much of each solution is needed? What do you think we're going to want to use to, what are these variables going to represent that we're going to choose? Last time it was the number of people for basic and the number of people for deluxe, right? This time, what is the question asking? How much of each
Water
are needed?
and salt.
So G.
Water and the salt solution. So let's let W equal the amount of water, right? And let's let this one just be, I don't like to use S's because they look like 5s. So I'm not going to use S. Let's use, I don't know, something else.
A.
A. A is going to represent the amount of the salt solution. Okay? Now, what do we know? When we mix them together, how much total are we supposed to get? How many gallons?
75. Wait.
Say it again.
75?
75. So we know that W plus A is supposed to equal 75, correct? Total of 75 gallons. Now here's the one part that's a little bit tricky. The second equation doesn't deal with the total amount. Remember how our last problem, the first equation dealt with how many people we had. The second equation dealt with the amount of money that they spent, right? So here our first equation is dealing with the amount of the two solutions, water and the salt solution. The second equation deals with how much salt is in each. Now, how much salt is in the pure water?
0.
0. So we don't have to worry about that. But when we're all done, or how much salt is in the this one? 10%. Now we don't use 10%. What do we use instead of 10%? We have to change it to a decimal, and it's 0.1. Okay? So 0.1 times A is the amount of salt that we're dumping into this 75 gallons of stuff, right? How much salt is going to be in it after we're done dumping it in? Well, this, right? That's the only salt we're putting in. The rest is all pure water, okay? But what's the total supposed to be? Well, the total is supposed to be, in our new amount here, 75 gallons, 3% salt, right? So to figure that out, how would you figure out what 3% of 75 is? Yeah, what math? Multiplication. Of, right? Of kind of means times. If you think back to, depending on when you learn this in elementary school, of means times, is means equals, and all these different things. So 3% of 75. So there's my 75. I'm going to multiply by 3%. But how do I have to write 3%? 0.03. Okay, this is probably the tougher one because it's not as obvious that you're just adding 2 together and get 75. Here, we have to remember the only salt that we're putting in is from this one. It's 10% salt times the amount that we're putting in from that container. And when we're all done, we're going to have 75 gallons. That is now going to be 3% salt. This is a perfect example to use substitution, right? Because the second equation only has an A in it. Does that make sense? So let's simplify. 0.1a equals, what do we get when we multiply 0.03 times 75? I think it's, somebody help me out, but I think it's 2.25. Is
Yes.
that right? Okay. Then what do we have to do to figure out what a equals? Divide by 0.1. And we get a equals 22.5, I believe. Is that correct?
Yes.
Okay. And what is that? That is an amount of gallons. So that tells us we're going to use 22.5 gallons of salt solution. Okay. Now we can go back up here. If A is 22.5, how are we going to figure out how much is water?
Replace the A with the 22. Okay.
Correct. Replace the A with the 22.5 and do what? This one wasn't quite as easy. We probably couldn't do this one in our heads, right? With like the 13 and the 14. But what do we do mathematically? What do we have to do here?
Minus the
Subtract. Yep. Subtract 22.5. We get W equals, I'm going to say 52.5. Is that correct? Okay. So we get 52.5 gallons of pure water. Okay. That one was, like I said, that one was a little bit trickier because you had to, something we're maybe not quite as used to, right? Now, if you did chemistry a lot, you'd be like, oh, this is easy. I just whip these two together and figure it out. Okay. But that is our solution there. And again, make sure you identify what that means. Okay. So that is the end of our linear systems. You're going to have 8 problems to do there. So make sure you take some time. Like I said, I think there's probably a couple word problems, 2 or 3, and then the rest will be the systems from the beginning. So again, make sure you try those.